the Sci-AI Podcast. This is episode number 5, and today I have a great guest with me whose name is Rudra Sekhri. Rudra is an astronomer, an astrophysicist, a young child of only 14 years of age, which is truly remarkable what he has accomplished so far in his life already. So it'll be a great honor to, have him on this podcast and listen to his views on science, planets, space travel, AI, and so many other stuff. Rudra, welcome to this podcast.
Thank you much. Thank you so much, Vivek.
Yeah. Please go ahead and introduce yourself a little bit, and then we can jump over to some of the topics we had in mind.
Yeah. So, hi everyone. My name is Rudra. As Vivek mentioned, I'm a 14-year-old student, passionate in science, technology, engineering, and mathematics, which can be abbreviated as STEM. And over these past few years, been working with astronomers from across Australia and even around the world, in just discovering these fast radio bursts, or FRBs as Vivek mentioned, and also understanding these weird stars known as pulsars, which we'll get more into later in this podcast. I'm also the author of a climate change book, The Earth Needs You, as I'm also very passionate about climate change. And yeah, that's just a brief description about myself. We'll get more into some of the other stuff I do later on in the podcast.
Excellent. Can you also share where are you based, what and where do you do your research and everything?
Yeah. So I'm based here in Australia, specifically Melbourne, and I do research with astronomers from the Swinburne University of Technology, and the University of Sydney, up at the Molonglo Observatory Synthesis Telescope. Now, this telescope is located in Canberra, which is the capital of Australia, and it's just a few hundred kilometers north of Melbourne. So, yeah, it's
Fantastic.
one of the biggest telescopes in the Southern Hemisphere.
Oh, wow. That's great to know.
Yeah.
Fantastic. Okay, so let's jump on to some of the questions I have for you, Rudra. How did you get into astronomy, pulsar astronomy, and FRB at such a young
radio bursts?
Fast radio bursts at such a young age of 14. What was your motivation, and when did you actually start studying about these? Who are your heroes and motivators in this field of science and research?
So I actually got interested in astronomy when I was roughly 10 years old, and before then I was primarily interested in physics and mathematics. And back then I probably only knew maybe a couple of things about astronomy. For example, that we live in the Milky Way galaxy, towards the outer edges of the Milky Way galaxy. That's a general fact which most people know of. But then, over time, I started getting interested in astronomy, and then, something just clicked for me, and then I was like, I want to become an astronomer. And ever since then, I've been, devouring resources on the internet, which we will discuss further later in the podcast. And then I was sort of stuck. I was stuck roughly 3 years ago, and I was like, okay, how do I apply what I already know about astronomy and astrophysics in the real world? And that's when I began researching with astronomers and research institutions from various universities across Australia and even internationally. And these projects often revolved around pulsars, fast radio bursts, and other really cool astronomy phenomenon like gravitational waves. And so one such organization was OSGRAV, or the Arc Center of Excellence for Gravitational Wave Discovery. This organization, as you can tell by its name, primarily focuses on gravitational waves, but they also observe other phenomena like neutron stars, pulsars, and fast radio bursts using telescopes like the Molonglo Observatory Synthesis Telescope, and even some more popular telescopes like the Square Kilometre Array here in Australia, or some of the telescopes in South Africa. Now, since joining Osgrave in 2018, I've been working with world-famous astronomers on various projects, and one of these projects was actually like maintaining a detailed record of pulsars. And for now you can think of pulsars as just like really weird neutron stars, stars made entirely of neutrons. And basically, this is what we call the pulsar timing program. We've also been actively working in the fast radio burst field, so discovering these really weird extragalactic events. And so just recently, actually, we detected a fast radio burst using the Molonglo Observatory Synthesis Telescope. And we've also just been upgrading the telescope over time and presenting that work in conferences such as the International Fast Radio Burst Conference of 2020. And my role in this upgrade is just predicting and measuring that sensitivity using AI models and complex calculations. This work, which was the upgrade of the Molonglo Observatory Synthesis Telescope, as I mentioned, was presented in the International Fast Radio Burst Conference. And this conference was centered around fast radio bursts and just some of the latest updates and discoveries on fast radio bursts. But not only that, I've also been working with organizations outside of Australia, and one such organization is the International Astronomy and Astrophysics Competition. Actually, just this year, I got the opportunity to become their ambassador, and I also, funnily enough, actually got the chance to participate in their competition and win the national award for Australia. So that was really, really, really nice. I believe everyone has their own personal heroes, and in this case, my personal heroes were actually, at first, the big scientists, the big science communicators that you would often see on TV, and these included people like Neil deGrasse Tyson, Brian Cox, Sean Carroll, Michio Kaku, Brian Greene, just to name a few. However, once I actually started doing astronomy, my main hero and motivator actually just became my mentor, which was Professor Chris Flynn. And Professor, if you're actually watching this podcast, I'd just like to say from deep down from my heart, I'd like to say thank you for all your support. And also just the fact that, you're just a wonderful man to work with. But yeah, that's pretty much all that I have to say about myself and how I got interested in astronomy.
Fantastic. And congratulations on winning that award for Australia. So proud of you. And also,
Thank you.
Some of my motivators and heroes are the same, like you mentioned, Neil deGrasse Tyson and Brian Cox, Brian Greene, Michio Kaku. Michio Kaku is just fascinating. He's amazing. All right. Let's go to the next one then. What does the study of FRBs, fast radio bursts, pulsar astronomy, and magnetars will do for humans and science? I mean, it's great what you've described about these topics, but how is it important for us humans? And will it help us detect signals from extragalactic regions?
Yeah. These are some great questions, Vivek, and I think the way I'll go about answering this question is I'll start off with defining or explaining what these objects are and what these events are. As I think by understanding what these objects are, we can better understand why these phenomena occur and why they are important to us. So let's start off with fast radio bursts, as it's the weirdest one of them all. Fast radio bursts, or FRBs, are actually millisecond bursts of energy in the radio spectrum of light. And usually what we find is that fast radio bursts actually tend to come from outside our galaxy. We are actually already detecting fast radio bursts from extragalactic regions. But this is kind of weird since we expect to detect much more powerful fast radio bursts from within our galaxy. But we just haven't seen something like that yet until very recently. And I believe that was in 2020. Fast radio bursts were actually discovered by a person called Duncan Lorimer back in 2007. So they're actually a very recent discovery. And since then, we've detected hundreds of fast radio bursts. And one such observatory in Canada called the Chime Observatory is able to detect dozens at a time. And it's just fascinating. Now, at first, many people thought that fast radio bursts were deliberate signals from aliens, but as we all know, scientists tend to reserve that theory to the last point because you can pretty much explain anything with aliens.
Mm.
Um, and so now we realize that based off that discovery, which I mentioned back in 2020, of a FRB, fast radio burst like signal within our Milky Way galaxy, the most likely theory is that fast radio burst is actually being caused by magnetars, which I'm just going to talk about right now. Um, Magnetars are actually very similar to neutron stars and pulsars. In fact, magnetars are a subcategory of pulsars. Sorry, not pulsars, neutron stars. Neutron stars are actually primarily made of neutrons with a small layer of plasma on its surface. And the reason why it's got such a structure is because neutron stars are crushed so tightly that all the protons and electrons literally merge together to form neutrons. And this is due to the immense pressure and density, which you just don't see on the surface. And as the neutron star spins, it creates giant magnetic fields, and these magnetic fields are due to the fact that electrically charged particles move in a certain way. And whenever electrically charged particles move, they generate a magnetic field. Um, and so these are just neutron stars, but magnetars are just the neutron stars with some of the strongest magnetic fields. They could be millions of times stronger than Earth's own magnetic field. I think sometimes even billions. Um, Pulsars are also a subcategory of neutron stars, except what happens is that their magnetic fields actually squeeze their radiation, their electromagnetic radiation, into these beams, and these beams sweep across the sky. And to a distant observer like us, it seems as if the pulsar turns on and then off. And you can think of them like lighthouses. And so, like, to a distant sailor, the lighthouse turns on and then off at a very periodic rate. And I think by understanding these phenomena, we can better understand, like, the stellar evolution, so the evolution of stars, the life cycle of stars, just understanding what these objects are in general. Um, but also it's just fascinating to know for us humans. As humans, we have been wondering about the universe for quite some time, and so I think it makes sense to also for us to also question, like, certain stuff about pulsars and fast radio bursts, because, like, this is very human to us. It's very human for us to ask questions and then get certain answers, and also formulate our own answers and theories. So that's what I think. That's what I personally think about, why we should observe these phenomena. Um, Now, before we move on to the next set of questions, I'd just like to mention how these objects, how do we actually observe these objects and events? Because we actually observe them in the radio spectrum of light. And as you can tell, we use radio astronomy, and radio astronomy is a part of astronomy where we focus on the radio spectrum of light. And this is extremely important if you want to look at, for example, like, hydrogen emissions in galaxies, or you want to look at, like, cosmological redshift, which can be used to determine the age of the universe, and also these other events which I've been talking about. Um, and so we can use radio astronomy to understand more about these objects, because this is the part of the electromagnetic spectrum where these objects tend to emit the most. And so that's what we at the Molonglo Observatory Synthesis Telescope are doing. This telescope is actually a radio telescope. And so we observe these pulsars and fast radio bursts, like, all the time. It's one of our specialities, if you will. And the funny thing is that we can actually see phone calls and other human-related activity in in this data sometimes, and it's really funny to see that, because it just sort of screws up our data, and, like, we're like, oh no, we have to clean up the data. So yeah.
Right. Great. That's a great description of FRBs and pulsar and magnetars. So my next question is, what is pulsar astronomy and how is it related to neutron stars? I mean, how are the clocks? Is it because they are really precise? Can you talk about it?
Yeah, so again, really great questions, and I'll just briefly mention what I described earlier. and that was just that like pulsars are a subcategory of neutron stars, and that neutron stars are primarily made of neutrons with a layer of plasma on its surface, and so when the pulsar spins, it creates giant magnetic fields from moving electrically charged particles, and these magnetic fields can be like hundreds of thousands to even millions of times stronger than Earth's own magnetic field. You can think of them as some of the most strongest bar magnets in the universe. Um, so yeah, it's
Wow.
pretty insane. Um, Now, you can think of pulsars as lighthouses, and again, if you recall, the analogy which I gave with this sailor looking at a lighthouse, then to a sailor, the lighthouse turns on and then off at a very periodic rate. And the thing with pulsars is, yes, they are also very periodic. In fact, they're so periodic that some people tend to think of them as really precise clocks. Um, and so every time you see the
Hmm.
electromagnetic beam, it's just like, it's sort of like that tick on a clock. And so you've got like that tick-tock pattern going on, and yeah, you've got yourself a really precise clock. In fact, they're so precise that sometimes myself, scientists, including myself, believe that pulsars are some of the most precise, naturally occurring clocks in the universe. And with precise, and with these precise pulsars, you can actually use them as instruments to be able to observe very cool phenomenon like gravitational waves. Of course, over the course of time, the pulsar will eventually begin to slow down, and we see this pretty much for all old pulsars. Their spin period, or how fast they spin, actually starts to decrease very, very, very slowly over time. And over the course of a human lifetime, that's barely negligible. But it's something which we take into consideration. Another thing is that pulsars can glitch, and what I mean by glitch is that they can periodically speed up this spin period, and we actually detected one just a couple of weeks ago, actually, a glitch in the pulsar, in the Vela pulsar, which is one of the brightest pulsars in the southern hemisphere. And so, it's really interesting to know these properties and to understand why pulsars glitch. And there are some really compelling theories out there, but for now, there's just not that one unifying theory that puts it all together. And so, but most of the time, pulsars do generally follow a very consistent periodic spin period, um, and that can be used to detect gravitational waves. Now, gravitational wave detectors such as LIGO use extremely precise instruments, and you can use pulsars as extremely precise instruments as well. For example, if you line up a bunch of pulsars in the Milky Way, right, and you observe them all at once, and you detect you detect this that some of these pulsars start to glitch. If they glitch in the right fashion, then you can use models to predict was there a gravitational wave that was passing through, and if so, how strong was it and what was it being caused by. And so these are some of the great science we can do um, with
How
pulsars.
Right. So how do you make these pulsars? Because I remember you said you can take any two stars in the galaxy and then make them as the endpoints of that detector. Can you talk about it a little bit?
Yeah. So what you can do, what you can do is you've got pulsars, and basically what you do is you observe them similar to the LIGO detector. A LIGO detector has got two arms like so, right? And so what you can do is you can do the same thing but on a galactic scale. And so you've got a line of
Right.
pulsars like this way in the vertical direction, and a line of pulsars in the horizontal direction.
Right.
Now, let me be clear that these directions can actually be completely arbitrary, so you
Yes.
can define them however you want. Just
Exactly.
remember that they should
Right.
be perpendicular to each other, i.e., they
Right.
should form a 90-degree angle with each other. And
Mm-hmm.
basically, what you do is you use those pulsars to determine if there's a change in phase. And this change in phase could be a change in spin period, a pulsar glitch. In terms of LIGO, it uses extremely precise clocks and measuring devices to be able to detect changes in phase. with different wavelengths of light. And if there is a change in phase, then that means that something passed through, and this could be like like some human activity, or it could be a gravitational wave. Um,
Mhm.
so yeah, that's just like, one way as to how you could go about like, using pulsars. Obviously, there are many other ways to do so. But yeah, in terms of how pulsars actually form, I'll just quickly mention that pulsars form by supernovae. So what happens is that a really giant star, like ten times, or like a dozen times more massive than our sun, it explodes in a supernovae, and that's because what happens is that the star actually collapses in on itself, and that collapse causes an immense amount of pressure, and that immense amount of pressure releases a lot of energy within the star's core, causing like a giant explosion. And so what happens is that you're left with just like a single ball, and this is the remnants of that supernovae, which can either be a pulsar or a black hole. But sometimes it's like but sometimes it's pulsars, and sometimes it's black holes. Yeah. Um,
Fantastic.
yeah. Um, yeah, I'll just also quickly mention that, like, where just a bit of history as to how pulsar astronomy actually got started,
Mhm.
because I really find this story very funny. And that is that
Mhm.
pulsar astronomy actually first started in 1967, and it was started by a radio astronomer by the name of Jocelyn Bell. And at first, she thought she was seeing deliberate attempts from contact from aliens, but as we all know, it's never aliens until it's aliens. In
Right.
fact, she was so convinced that she named one of the first pulsars LGM-1, also known as Little Green Men 1.
Mhm.
However, as later analysis showed, she had really discovered a new type of neutron star, and the search was on to find as many of them as possible. Since then, we've found like 2,657 pulsars, and that's mind-boggling. And
Yeah.
we still might find more. Pulsar astronomy is a really active field of astronomy, filled with mysteries and discoveries. Um, yeah, and in fact, most of these 2,600 pulsars are within our own galaxy. So that's kind of really
Wow.
interesting to see.
Right. Right. And so going into future, we might be able to go venture out into other galaxies and find more pulsars there. If we can find so many already in our own galaxy. That's fascinating
Yeah,
stuff.
yeah.
Great job,
Yeah,
Rudra.
it's
Yeah.
thank you so much.
You were saying something? You want to finish it?
No, I was just saying thank you so much.
Yeah. Okay, great. Um, do you think that it is possible that other civilizations are so advanced that they could use fast radio bursts and sending it to our galaxy like we are trying to do it? But due to the vastness of space and distance between us and their galaxy, I mean, some of them are many, many million light years away, right? It can never reach us, their signals. So, how does the FRBs travel, and what is the speed of travel?
So I'll first answer that last question which you posed, which was that, like, what are FR like, how does the FRB travel and what is their speed? Now FRB, as you can tell by its name, is a fast radio burst, and radio is a form of electromagnetic radiation, and as we all know, electromagnetic radiation travels at the speed of light in a vacuum. So, if you do detect a fast radio burst from, say, a nearby galaxy a few million light years away, that fast radio burst event actually happened 2 million years ago, which is very, very, very interesting. Um,
Yeah.
but in terms of alien civilizations contacting us, I couldn't actually see why not. I couldn't see why not. Aliens would go ahead and, create these giant beacons to send us, deliberate signals in the form of fast radio bursts. But if an alien civilization was to do so, it was advanced enough and has the means to communicate with us through fast radio bursts, then they certainly could. But would they? That's actually a very interesting point to raise. Like, imagine ourselves as as an advanced civilization, we colonized the star systems. We're collecting so much energy through Dyson spheres and Dyson swarms. Um, you know, would we want to waste that energy, like, deliberately sending signals to, aliens, even though we are not sure that that aliens exist or not? Like, that's
Right.
just one of the things which comes to my mind is these socio-economic factors. And that is that, like, for such a signaling option, there's just going to be way too much cost involved and way too much energy wasted. And this could be used in much more effective ways, such as, you know, colonizing the galaxy and stuff like that. Instead, like, would aliens really want to spend all those resources just trying to communicate with something that might not even exist? Like that's just the question which I've got in my mind. I'm not actually trying to downplay the idea that aliens don't exist. I think aliens do exist. It's just that aliens would probably not have the time nor put the effort in actually doing this sort of implementation. And so I'd like to sort of like, shift the focus on us humans. Like, how could we signal aliens? And this can sort of help us determine, like, what aliens might do with us, because we can assume certain things about aliens, that aliens do not want to waste resources. They are on occasions very competitive, but sometimes they're also cooperative, just like us humans. So one of the signaling options is to possibly set up structures around our star that look distinctly artificial. And to an alien astronomer, it looks as if, like, something artificial is going around this star, and they can deduce that humans are creating a presence in their solar system. And this could be setting up like a Dyson sphere or a Dyson swarm. Um, and this is a very apparent form or means of communicating. However, these
Mhm.
signals would only reach probably a few hundred light years, or probably like a few hundred to a few thousand star systems. But that's probably enough to, like, at least get like the chance of, like, aliens being able to see such stuff. Um,
Mhm.
and just another thing on fast radio bursts and aliens contacting us. Think about the probability that alien signals will be actually, like, reaching us from millions or billions of light years away. Like, just take a moment to fathom that. Like,
Yes.
it would be ridiculously low. Like, the probability would
Right.
be ridiculously low. And so, like, not only would the aliens have to, like, create lots of beacons, but they would also have to have incredible chance to be able for their signals to reach us and us to actually detect them. Um, like, and just also another thing, like, we're discovering fast radio bursts all across the night sky. So if
Mhm.
that is true, if aliens are sending fast radio burst signals from, like, multiple galaxies, then there must be multiple advanced alien civilizations. Yeah, we just don't see evidence of that.
Right.
Unless you're talking about Area 51, which in this case, like, sure, believe whatever you want about aliens.
Right.
Um, but, like, in just my personal opinion, I'm a person who's a very logical person, and I feel like, I feel like if this was a possibility, like, it would just be incredibly, like, improbable. And I feel like there's a natural explanation to accompany this. In fact, we did discover a fast radio burst like signal in our own galaxy, and we now think that fast radio bursts are coming from magnetars. So
Mm.
yeah, that's pretty much all that I have to say about that.
Okay. Let's move on to the next question then. What can you share about astronomy with young people in the world who would like to get into the field of astronomy and astrophysics, right from their early, formative ages, like yourself? What is your advice for them?
Yeah. Um, so I personally feel that there are different ways of approaching a new topic, such as astronomy and astrophysics, and there are various ways to learn more about that. My way was actually just slowly going through content on the internet and just learn about the universe which we live in. For yourself, it might be like, taking photos of the night sky and analyzing the data you collect from your telescope. But for others, it might just be attending lectures. But I could go on and on and on. And the
Right.
truth is, everyone has a different way of, approaching the same topic. Now, if you really do want to get into astronomy and astrophysics and specifically learn the basics of, how astronomy works, how astrophysics works, and, just some of the base stuff, then there are some really good books which you can get into that I'll mention just in a couple of seconds. And these include A Brief History of Time by Stephen Hawking, Brief Answers to the Big Questions by Stephen Hawking, Astrophysics for People in a Hurry by Neil deGrasse Tyson. I believe there are a couple of more which I cannot remember off the top of my head. But yeah, you
It's
can
all
just
right. We
find all
can
of this
put it
stuff
in
on the
the we can put it
yeah,
in the description as well of this video.
yeah,
No?
yeah. Check out the description, and also there's a really nice thumbs up button next to it. Please go click that as well. Um, um,
Thank you.
however, if However, if you are not a person who is interested in reading books and would like to watch some videos instead, or have a visual way of learning the concepts in astronomy, then I've got some really good YouTube channels for you. So one of them includes PBS space. Let me repeat that. One of them is PBS Spacetime. This is a YouTube channel that is really centered around a hardcore astronomy and astrophysics, and I believe this is one of the most popular astronomy and astrophysics YouTube channels out there. And they go really deep into research papers and complex astrophysics concepts, astronomy observations, and much, much, much more. Another example is Minute Physics, and as you can tell by the name, Minute Physics aims to explain physics in simple, small, minute-sized chunks. It's a really great YouTube channel if you want to learn stuff quickly, um, and just learn something really cool really fast. Another YouTube channel or professor which I would recommend online is Dr. Becky. Now, Dr. Becky is actually an astrophysicist who works around black hole astronomy, and she mainly talks about the latest news in astronomy and space science. She also dives really deep into research papers and astrophysics concepts, especially when they relate to cosmology or the study of the entire universe. Um, there's a really great course on YouTube for free, which is called Crash Course Astronomy. And as the name suggests, it is a crash course on astronomy. If you do want to learn the basics of astronomy, then this is a free course on YouTube that I recommend. And this course breaks down certain concepts into bite-sized 10-minute videos, which you can watch one by one. Um, Another great YouTube channel is actually Path G. Now, Path is actually a university student who is studying astrophysics in the UK, I believe. Uh, he is studying astrophysics in the UK and aims to explain the physics and mathematics behind astrophysics as clearly and concisely as possible. It's a great YouTube channel if you want to check it out. However, there are many more which I could go into. Um, there are other resources that can help you excel in astronomy and astrophysics. These can be competitions, online lectures, and more. Some of these include the Feynman lectures on physics. These are available online if you do want to have a read of them. Richard Feynman, again, one of my personal heroes. He was not only a great physicist but also a great teacher, and that's one of the qualities many scientists have as well. The International and Astronomy Astrophysics competition is just another competition which you could get involved in. It's a great competition to get involved in if you do want to compete against many other talented students in astronomy and astrophysics. There's also astronomy lectures just nearby. I know due to coronavirus, many of these lectures have been moved online, and these are now available for the public to watch as well. But there are many more which I could go into, and these are just some of the resources online, and all of these are completely free, so no costs required. But I feel like if you do want to learn astronomy, I feel like the best way to do so is to actually just go outside and gaze up at the beauty and complexity of the universe and wonder how and why it became this way. I believe that anyone can become an astronomer and discover something new about the universe. And in fact, we see that with amateur astronomers discovering new moons around Jupiter.
Okay, great. Let's get on to the next question then. Can we ever be able to travel beyond our solar system, Rudra, or our galaxy? This, when we know that all galaxies are traveling apart from each other with the speed of light or more, because as we know, space is expanding. If that is the case, will we ever be able to travel so far, or it's going to be generations after generations living on a spaceship, and then after thousands of years, they would reach the other star system where we may find a habitable planet? Or will we send only the most advanced robots to other planets with eggs and make them so advanced that the robots will help make new humans at those planets? So what are the methods of travel possible in the future, like about 200 or 300 years from now in the future?
Yeah. So before I actually go ahead and answer those questions, I've just got 2 points to mention, and that is that one, we will unfortunately not be a Star Wars empire. Sorry, guys, it's just not going to be a reality. We will not travel faster than the speed of light. But secondly, it's true, the space itself is expanding, and it's not actually galaxies moving apart from each other. It's just that space itself is expanding. According to Einstein's theory of general relativity, things cannot move faster than the speed of light through space, but space itself can expand at whatever speed it
Mm.
wants to, including faster than the speed of light. That's why we see some galaxies racing away from us faster than the speed of light. I think we've already traveled beyond the solar system, at least in my opinion. We've already sent two probes, Voyager 1 and Voyager 2, and they've already made it into interstellar space from a technical perspective, which means that they are outside the solar system. New Horizons, which was a probe launched in 2015, is also on its way out into interstellar space, and Pioneer 11 and Pioneer 10, while inactive, are also at the farthest reaches of the solar system. In conclusion, we've already sent quite a lot of probes outside our solar system. In fact, if we used current technology and no fancy Star Wars warp drives, then we could colonize the entire galaxy within 10 to 20 million years. Now, I know that might sound like a lot, but compared to the age of the Milky Way itself, which is 10 billion years, that's actually just a blink of an eye. Um,
Yeah.
However, transporting humans to other star systems is expensive. It's going to require a lot of resources and a lot of energy. And so, you know, it's just going to require, lots of time and lots of effort and possibly even generations upon generations on those starships, as you mentioned.
Mm.
Um, for it might make sense, as you mentioned, to send what are called von Neumann probes or self-replicating robots to those planets to explore them for us and colonize the galaxy that way. Um, and in fact, it seems like a legitimate idea. We have now reached such a stage with artificial intelligence that it could be possible that probes can build themselves with, no fancy, magic involved. This is actually an alternative yet promising idea. Um, but when it comes to colonizing other galaxies, I just have to be a little bit unfortunate in the fact that we cannot feasibly colonize other galaxies as it just takes too long. To be fair, if we really wanted to, we can colonize nearby galaxies such as the Andromeda Galaxy, Triangulum Galaxy, and other smaller galaxies within our local group. It would just take millions, possibly billions of years to reach those galaxies, as again, as you mentioned, galaxies are traveling away faster. Galaxies are traveling away from us, and the universe is expanding. Now, the boundary of the observable universe, the universe which we can see, is the particle horizon. And the thing is that while we can see all these galaxies, we can only reach a fraction of them if we travel at the speed of light. So right now, if you look at some of the most distant galaxies with, say, the Hubble Space Telescope, we will never be able to reach those galaxies, unfortunately. There's actually
Mm.
another horizon which is defined inside the particle horizon, which I like to call the cosmic horizon, and that's how far we can reach out if our spaceships traveled at the speed of light. Um, and so this cosmic horizon is roughly 16 billion light years in radius, or 32 billion light years in diameter. And so, technically
Wow.
speaking, we could only reach probably a third of the observable universe, which is just tiny. And it makes us insignificant. But don't worry, we're not
Mm.
insignificant. We are really smart apes. Um, in the next 200 to 300 years, we'll probably see new technologies developing, such as fusion technology. We technically already have fusion technology in the form of nuclear bombs. And while space treaties prevent nuclear testing in space, technically we can, redact those treaties. We can get rid of them so that we can use nuclear bombs to propel our spaceships. Yeah, I know, Cold War is coming back. So we can use thermonuclear fusion from these nuclear bombs to power our spacecraft. We could also use sustained fusion, which is continuous fusion, and this will be coming up soon within the next few decades. Once we start producing something called antimatter in really large quantities, we can also create antimatter drives that essentially smash regular matter with antimatter and release a bunch of energy in the process, which can propel our starships forward. Um, Another idea, which many scientists are thinking of, is using something called light sails, and these light sails essentially use light from the sun to push them forward, and there's no fuel required. Um, and so these are just really, really, really cool ideas. I think any interstellar journey is actually just going to be a multi-generational journey, as the
Mm.
distance between stars is huge. And to reduce the time it takes to reach stars, we need to develop these new technologies. Um, I'm not going to go into warp drives, specifically the Alcubierre warp drive, as a mechanism for transportation, as it's really just a bunch of mathematical mess. Yes, I said that. It's a mathematical mess. And the reason why these warp drives don't work is because in order for them to work, we need something called exotic matter, or matter that produces anti-gravity, which is just insane and completely idiotic. Um,
Mm.
and so this negative matter and negative energy would warp space-time in such a way that space-time contracts in front of the spaceship and then expands behind the spaceship. Now, if you don't know what space-time is, it's just a mathematical medium described by Einstein's theory of general relativity, and it's the reason why gravity occurs. But moreover, not only will this not work because, like, negative matter won't exist, even if it does exist, it will cause time paradoxes, and it will also produce a lot of Hawking radiation, which might roast everyone inside the spaceship, which is just absolutely insane. But in conclusion, the next 200 to 300 years, we'll probably see ourselves using a mixture of traditional fuel, possibly electrical propulsion, and possibly some fusion technology as well, and possibly even start expanding out to nearby star systems such as Proxima Centauri.
Fantastic. Great explanation. All right, then. So, how do you teach astronomy to kids in your school or university? If I have a long range telescope, let's say a refractor one, where should I learn to focus and see the nearest galaxies and planets? Or do you have some other suggestion on it?
Yeah. So, personally, I actually wouldn't even start with a telescope. I would actually start off even simpler, and this is one of the first mistakes that many astronomers see with, beginners, and this included my mentor, Professor Chris Flynn. He actually saw the same mistake which I was making, and that was, getting a telescope. And this is because many people associate a telescope with professional astronomy, when it's really not. You can do decent astronomy with binoculars and other refractors, all at the fraction of a cost. And and to be honest, the best kind of astronomy is actually with your own eyes. Um, of course, a telescope can magnify and resolve extremely fine objects for you, but I just find it much more engaging to just gaze up and take everything in. So I like to actually teach astronomy in a chronological order. Start off with the things which we knew for thousands of years, and then move on to the more recent stuff. First, what I would do is I would actually take students on a dark night and tell them to gaze up at the night sky, and then we would start to identify patterns such as the Milky Way band, some of the constellations, such as Orion, Scorpius, etc. and then also identifying planets and stuff like that. And even depending on how much light pollution there is, we might even be able to see some faint nebulae. And this gets the audience familiar with the night sky. I usually bring these students out maybe once or twice per week for 2 to 3 weeks, just to get them familiar with the night sky and some of the brightest objects, and also just some of the slow changes you see in the night sky. By gazing up at the night sky, it shows how insignificant we are, um, as humans in the entire cosmos. But after all, we're just one human species on one planet, on one of the billions, potentially trillions of galaxies. And by realizing this, we realize truly how beautiful our universe is. And yes, I know, being insignificant sounds kind of a bummer, but the truth is, we are not actually as significant as we think. We could be the only observers in the entire universe, and so feel grateful for that.
Yeah.
What I usually do is then spend a few lessons going through the basics of the universe. This includes learning about where the Earth is on a cosmic scale. For example, the Earth is a part of the solar system, which is a part of the Milky Way galaxy, which is a part of the local group, and so on and so forth. I also usually go through the basics of the solar system, and this is what people are most familiar with. This is because usually many people have heard of NASA missions within the solar system, especially missions to Mars. And it seems like the great place to start. And once we go through the solar system, we then start linking everything together. So, for example, if we are learning about the sun, we would then start to talk about spectral properties. We would then start to talk about, like, the composition of stars, how stars are formed, the life cycle of stars, and so on and so forth. Different types of stars. These are just examples.
Mm.
And this just makes it easier for things to connect, for students who are learning astronomy, and it's sort of like a jigsaw puzzle for them. Um, After that, we just do a few Q&A sessions with students, and they just basically just ask me any questions they have, and I answer by either providing some resources or just going out with a direct answer. And this is sort of like a Q&A session, and basically unlocks the students' curiosity and allows them to think outside the box. Of course, there are other ways of teaching astronomy. An organization called Space India, which I got in contact with last year, uses a project-based learning system to teach students astronomy. This method uses projects as a way to teach students how to formulate their own science experiments and then test them and get results. I personally do love project-based learning systems, and I feel like we are transitioning our way from the traditional way of learning, which is tests and exams, to project-based teaching methods. As a young astronomer who's still learning how to teach, I think that teachers and education systems should actually take students' feedback into account so that they can teach their content more effectively, without their classes seeming too boring for their students. Um, I do this all the time, in fact, and students provide me with feedback, and I incorporate different ways of teaching so that everyone can learn. Because the truth is, I'm here to empower others, and I think that's what schools need to do as well. Once you've got some experience with doing some astronomy with just your eyes, then you could start getting a Star Tracker app on your phone. Um, and we would recommend binoculars as astronomers. The reason why is because binoculars are easier to handle than telescopes, and they only cost a fraction as much as the same. They also only cost a fraction of a telescope, and they achieve the same results. Also, if you're not interested in astronomy, then you can use those binoculars for bird watching as well. So, it's
Yeah.
just really interesting to see how students, like, interact and, discuss and brainstorm, new ways of thinking about astronomy.
Fantastic. That's a great description, Rudra. So, as per you, what is time? And is it an emergent phenomena of the Big Bang? So simply put, was there time before Big Bang? And if there was, then how is it logically possible? Yeah.
Yeah. So, I was actually kind of expecting this question because I hear many people ask this question, especially if they've read general relativity. And I'll get more into general relativity later. Um, but again, I personally like to go through a chronological order. So let's start with, the first descriptions of time. Time was actually thought to be universal, and that meant that it was the same time everywhere. And this is how Galileo derived his theory of Galilean relativity, and how Isaac Newton derived his laws of motion. Time was thought to be absolute, unlike space, which was thought to be relative and still is relative. That means that basically motion through space is relative to the observer, and there is no universal observer. But then came Einstein, and of course he has to take physics and put it on its head. Einstein was actually working at a patent office when he developed his theory of special relativity, and the most likely source of this inspiration for this magnificent work were the patents he received on clocks and synchronization. Einstein became fascinated by finding out, like, is there a way we can use physics to prove that you can synchronize two clocks at the same time? And it turns out, based on his special theory of relativity and the two postulates which he formed, there is none. There is no way. And so there is no way you can actually synchronize two clocks simultaneously, no matter how hard you tried. In other words, time is not absolute, but rather it is also relative to the observer. Each observer only sees relative motion, but also experiences relative time. And since the distance between 2 points and the time between two events is different, time dilation and length contraction exist. And this has been proven in multiple areas, such as satellites, GPS, and so on and so forth. In fact, without Einstein's theory of special and general relativity, GPS would actually provide you with the wrong location, and it could be kilometers off in terms of its location. And this is the reason why time dilation and length contraction exist, is because in one of Einstein's postulates, he stated that the speed of light is constant for all observers, and by assuming that, all of this fell into place, and that caused this is it okay if I
It's
can
okay.
repeat that? I'll repeat that.
It's all
Yeah,
right.
yeah,
Yes.
yeah. Um, because of this postulate that light is constant for all observers, specifically the speed of light is constant for all observers, that just shows that time dilation and length contraction is true, and this has been proven by experiments. However, it turns out that there's actually something that is absolute, um, and it took Einstein another 10 years to figure this out. Now, the problem with having everything relative, like space and time, is that cause and effect won't work. It just breaks down. And
Mhm.
so, if cause and effect doesn't work, then, how is the universe going to work? And so, there must be something that is absolute, that defines cause and effect. And it took Einstein 10 years to figure this out. And he published his results in 1915 in Einstein's theory of general relativity. And not only did he find out that gravity exists, and gravity exists because of curvature in space-time, but he also figured out that space and time are actually one interconnected medium, space-time. Now, space-time is a four-dimensional mathematical medium that bends due to objects in that space-time. As some famous physicists put it, space-time tells matter how to move, and matter tells space-time how to curve. In this space-time, time is just an extra dimension, and basically you can go up, down, left, right, back, forth, and then forwards in time. Actually, in this space-time, in this four-dimensional space-time, while space and time are relative, there is something that is absolute, and that is called the space-time interval between those two events. So an event is defined by a location, a spatial location, but also an associated time. And the distance between these two events is the same no matter which observer is observing those two events. And this preserves cause and effect, and the universe is maintained, and we are all still alive. The problem is that physicists, mathematicians, and other great thinkers have conflicting ideas on what time really is, as it actually is on the brink between, science and philosophy. And I'm not a philosopher, so I've got no experience in, questioning stuff and postulating answers. But one such solution to defining what exactly time is that, time is just one of those extra dimensions. And with this extra dimension, you get an extra degree of movement. And so the past, present, and future exist simultaneously. And this is called the block universe. And at first, it seemed to make sense because it made sense with Einstein's theory of general relativity. But the problem is that we can remember the past, we can experience the future, experience the present, sorry, and we can predict the future, but not actually remember it or experience it ourselves. And so there's this difference between past, present, and future, which just does not exist in the block universe. Um, Other ideas include the fact that time only exists in the present, so there's only the present, and the past and future are only figments of our imagination and memory. But I
Mm,
personally think that there are other issues involved with that as well. For example, just the fact that, Einstein's theory of general relativity states that time is a dimension, which means you should have some degree of movement within that dimension, but that instantaneous time universe just doesn't provide that. Did time exist before the universe? Well, that's actually a highly philosophical question. And according to Einstein's theory of general relativity, space and time are interconnected, and space-time was created during the Big Bang. So, you know, from a scientific perspective, time was created at the Big Bang. But was there a more universal time that existed before the universe? I don't know.
mm,
Some people say yes, some people say no. According to some scholars, there exist two forms of time. One is the space-time, the time which is interconnected with space, and then there's also a much more, universal time, a time which has existed forever, and the universe is just is just in that time frame, and it's just existing in that time frame. But it's a possibility. Can we prove it? I don't know. It's just really highly philosophical.
but that's a great answer, Rudra, because science also has its limitations, right? We cannot prove everything right away or right now, but we can
Yeah,
hypothesize it and then start experimenting and starts to prove some facts. Great
exactly. And
answer.
I think, yeah, yeah. And
Mm,
just to expand on
please
that
continue.
point, I think that's the reason why, religion exists, because
Yeah,
some stuff is just not explained by science. And
right.
people tend to have faith in, certain things, like, for example, God created the universe and stuff like that. And, it's great to believe in all this stuff. Um, but there needs to be some form of scientific consensus that allows us to, determine a a scientific cause for some of these natural events. For example, we still don't know why the Big Bang was made. Probably a possibility is that it was created due to quantum mechanical events. um, you know it's just something which we just don't know yet, and this is where religion comes into play and says, well, God created the universe. But we can definitely say for sure that science does prove that the Earth is a sphere, not flat. So,
So, will we in the future, thanks to synthetic biology, be able to live forever? Because I have read that scientists are working on finding out how to stop aging by finding out how to manipulate cells in our body to never decay, because it is the cells in our body who starts decaying as we grow older and then we die. So, or do you think we will extinct by the natural extinction process of nature, or nuke ourselves, or get extincted because of viruses? Coronavirus is one great example of a pandemic, and or perhaps we get decimated by an alien civilization. So, what do you think?
um, so, um, so I personally think that synthetic biology is on its way to stop aging, possibly even to reverse it. And this is actually a very interesting point to make. Let me be clear, and I'm sure everyone on this planet will agree. We humans hate dying. Yeah, we humans hate to die, and let alone the
Right.
feeling of dying. In fact, we fear that we will die, even though we've got like 80 years before that will happen. And so, as a result, many humans would love to live forever. Now, we've reached a stage where we can try to do just that with synthetic biology, and I should probably point out that synthetic biology and other research will not be able to stop humans from dying of unnatural causes. For example, a pandemic, right? Even though it might have a natural or unnatural, cause. So like, coronavirus might have, come from animals or come from a lab. I don't know. Um, you know, it's because of human activity that caused that virus to go from, to come from that original source into humans, and so that's just an unnatural cause of human death. Another example is just a car accident. So, humans are dying in a car accident. That's unnatural, and so synthetic biology won't be able to stop that. The idea of slowing down aging is to actually slow down the mutations of cells, specifically the mutation of DNA, and slowing down that decay of DNA and other essential molecules in cells. Another thing which we need to do is, slow down those random mutations, and slowing down these random mutations can actually slow down the rate at which cancer develops. Um, and so by, preventing cancer and preventing these mutations, a human can live more can still live a healthy lifestyle, even if they're like, 90 years old or something like that. And this is something which we want to do. We want to live forever, because this will actually apply really well when it comes to colonizing other star systems. As I mentioned, if we expect that humans are going to live for 80 years, then we would require like, 3 to 4 civil generations, just so that like, we can reach the nearest star system and be able to start a colony there. But if we slow down aging, then humans might be able to live for, 200 years or something like that, and that will dramatically reduce the amount of resources we need to send humans to other planets and other star systems. But it will just make things a little bit more easier from the logistics perspective. Um,
Right.
in terms of going extinct, I don't think we're going extinct anytime soon. There's 7 billion people of us. I think we're even reaching 8 billion now. I don't think we're going
Yeah.
to go extinct. Back when we had like a population of maybe like, a few hundred thousand, um, then there was a possibility of going extinct. In fact, there was actually a super volcanic eruption called the Toba eruption. I forgot what it's formally called, but essentially it decimated human civilization surrounding that area, and nearly all human life near that volcano just died. Only
Mhm.
like a few hundred were left. Um, but now that we've got 7 billion people of us, natural disasters will not cause any harm to humans. Sure, they might kill a few million people, but like, on the grand scheme of things, that's just a tiny percentage of the human population. I think that something which might cause human extinction is, nuclear threats. So like, nuclear Armageddon. Um, and another one could be like, pandemics, like you mentioned, especially unnatural pandemics. So pandemics caused by like, human research, especially human research that involves like, enhancing those viruses to make them more deadly to humans, so that we can like, protect against them and stuff like that. That might be like a potential um, source. Another one could just be like an asteroid impact. Another one could be a solar flare. But as long as we get off this planet and we start a colony somewhere else, human civilization will not die out anytime soon.
That's exactly right. That's what I wanted to get on to. Like, this is the reason why I love Michio Kaku. So he said one time that, dinosaurs didn't have a plan B. I mean, they lived for almost like 75 million years on this planet, but they did not have a plan B. And that's why, with an impact of an asteroid, just in a few seconds, all of them died. And that's it. We now just have the remains of them. Can we as humans take that risk when we are such an intelligent organism? So really like your point that, if we go on to another planets and other star systems, we are sort of multiplying ourselves to different places and sort of reducing the risk of extinction.
Yeah. And just on a quick, just wanted to expand upon
Sure,
that point really quickly.
sure.
Just the fact that like, if something does happen to Earth, then, those other colonies, will not be affected because they're not on Earth. Those colonies are not on Earth, and so those won't be
Absolutely.
affected. It would require an extremely set of unlikely events, which would mean like something happening on Earth and then an asteroid impact on say Mars, and so on and so forth, which are just pretty unlikely to happen one after
Correct.
the other, and kill off human civilization so completely. Um, so that's my personal thoughts. And no, we are not getting colonized by aliens, unfortunately.
Right. Great point. What are black holes and why are they created by the universe? Are they an anomaly? Can we ever be able to travel to other galaxies in our universe using the wormholes? Or is it only theoretical and it is not pragmatic as humans could barely travel to moon or maximum to Mars as of now? So are we saying quite far in the future it is possible? What do you think?
So, let me just briefly. So, what I'm going to do is I'm actually just going to briefly define what black holes are, because the thing is that I think they're being misrepresented in the media quite a lot. And so I'm just going to clear up on some of those misconceptions, and then talk about like, why are they created, and can we be able to travel through other universe to other galaxies in our universe through wormholes and other stuff like that. Now, let's start off with an example. Let's say you are a distant observer observing a black hole. Let's also say that I'm orbiting the black hole. I'm close to the black hole, but I'm not that close. According to your frame of reference, my clock appears to be ticking slower than yours, and this is due to gravitational time dilation from Einstein's theory of general relativity. A similar phenomenon actually happens on Earth, but just to a lesser degree. Now, let's say you throw something into the black hole, say your water bottle, and as the bottle races towards the black hole, it picks up speed, just like an apple falling towards the earth picks up speed. Um, but that is, however, until the water bottle actually gets really close to the black hole. According to the water bottle's frame of reference, it passes over the edge of the black hole. But to us outside observers, it seems as it seems as if yeah. Okay, I'll just take a quick
It's
break.
it's all right. Yeah.
Okay, so according to the water bottle's frame of reference, the bottle crosses the edge of the black hole. However, to us outside observers, it seems as if the water bottle actually slows down and then just hovers at the edge of the black hole, and it just doesn't progress after that point, even if we wait an infinite amount of time. This is freaky. According to outside observers, the bottle just doesn't progress after the edge of the black hole, which means that certain events in space-time do not happen in our frames of reference. But the weird thing is that a black hole is that set of events, according to the outside observers, that do not occur. Now, it's not a visibility issue that's causing, us to not be able to see those events. No, 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 no. It's because space-time is so weird inside black holes that those events simply are not seeable, are simply just simply do not occur in our frames of reference. Um, Now, the edge of the black hole is defined as the event horizon, and this is because the last event to which we outside observers can assign a when is on the event horizon, and this is just a really weird and freaky thing. Because usually you tend to think of black holes as like really massive objects, but if black holes are really massive and really heavy, then where does that mass even come from? Does the events inside the black hole somehow mimic mass, or do they actually have mass? Now,
Hmm.
this is a big problem because the thing is that nobody actually really knows where this mass comes from. The thing is that in Einstein's theory of general relativity, there exist idealized black holes, or black holes with simplified physics, and such black holes are in are in virtual mathematical universes which do not have any matter in them, even in the black hole. And so, if we are to come up with a definition as to where the black hole's mass comes from, then it should not only apply to realistic black holes, the ones which we see in our universe, but it should also apply to these idealized black holes. Now, let's move on to some
Mm.
misconceptions about black holes. Now, the first is that black holes suck stuff in. That's not actually true. If you replace the sun with a black hole, then Earth would orbit it just fine. That is, if the black hole had the same mass as the sun. Now, the reason why I believe this is why I believe this, misconception came to be, is that, um, it's just the fact that, once you're inside the black hole, you can never really actually get out. And I think, and the best way to explain why this is true is because the space-time inside a black hole is so weird that simply going back out is not an option. Space-time actually descends into the black hole faster than the speed of light, and it descends down into something called the singularity. And this is why stuff cannot go outside a black hole. If you had like powerful rockets and stuff like that, you could totally hover on the at the edge of a black hole, or even just a little further out. The Earth, as I mentioned, can orbit a black hole just fine. Um, so yeah, this is just one of the misconceptions which I see a lot. Another is that, black holes are black because not even light can escape their gravitational pull. Um, I think this misconception is sort of a little bit more subtle, and I feel like there's actually a slightly different reason as to why that occurs. It's just that when you've got like an object going into the black hole, as it slows down and hovers over the edge, that light is actually stretched out so much by the black hole's gravity that it's basically invisible to us. And so
Mm.
when I was mentioning that the water bottle would hover above the black hole and we would never see it progress, we would actually see the water bottle slowly turn red and then invisible because of that red shift. Um, Also, just another misconception is that the singularity of the black hole is infinitely dense. Nothing can be infinitely dense in space-time. Um, in fact, the singularity could just be thought of as a hole in space-time. So if space-time were paper, like an A4 sheet of paper, then the singularity would be a hole in that paper. Now, there are various different kinds of black holes, ranging from stationary black holes or Schwarzschild black holes. There are also rotating or charged black holes, supermassive black hole mergers, and so many, many, many more. And these black hole mergers can be seen through gravitational waves. Now, you can represent black holes in diagrams called space-time diagrams, and all the events around black holes can also be represented using those diagrams. And these similar diagrams to your XY grid. And so on the x-axis you've got like your time, and on your y-axis you've got one dimension of space. But there are other ways of representing black holes, and one example of that is actually a Penrose diagram. And
Mm.
a Penrose diagram can describe space-time, and when you do the geometry of showing a black hole on a Penrose diagram, and you do a little bit of math, you figure out that the Penrose diagram is slightly incomplete. It feels as if, the Penrose diagram needs to be expanded upon. And what you find is that you find that on the other side of the black hole, you actually find a parallel universe. And
Mm.
and then you also find a white hole fitting that Penrose diagram, which is just absolutely insane. And this is where wormholes come into play. Now, the
Yeah.
problem is that wormholes and white holes, frankly, probably don't exist. And the reason why is because wormholes need negative matter or anti-gravity to keep themselves open without them collapsing in on themselves. The same thing goes for white holes. And so these are just purely theoretical mathematical objects that just came out of Einstein's theories. Um, you know, with Einstein's field equations, which determine how space-time should curve when there's matter around it, and how matter should move when space-time is curved. Not only can you just solve the Einstein equations traditionally, but you could just come up with your own solution and then work backwards to see what conditions you would need in order for that solution to come
Mm.
out to work. And so that's what Alcubierre did. He actually did that for the Einstein field equations and found that you could create an Alcubierre warp drive. Um, but the problem is that wormholes just don't exist. They probably don't exist, and even if they do exist, they would cause one, time travel paradoxes, two, insane amounts of Hawking radiation, and three, they would require negative energy and or negative matter or anti-gravity, whatever you want to call it, which just doesn't exist.
Fantastic. Great answer.
Yeah. There are also a bunch of other misconceptions I could go into, but like, you know, that's just some of them about black holes. Another
Yeah.
example, which I'd briefly like to
Yes.
mention is, you know, tides. So for example, the tides, right?
Mm.
We think the reason why tides exist is because, like, you know, you've got the moon and then you've got the earth, and the moon's gravity pulls on the water. And like, you know, that's what causes the tides. But the problem is that that just doesn't work out. Like the moon's
Mm.
gravity, right, from that distance, right, 380,000 kilometers away, is just
Mm.
is just a million times smaller than Earth's own gravity, which is like, you know, kind of stupid to think about. Like, you know, why would, like, you know, the moon's gravity, which is a million times weaker than Earth's own gravity, you know, pull something up to form tides? And the reason why tides actually occur is that the moon actually squeezes the Earth. It doesn't pull it, it squeezes the Earth. And this is because of frames of reference. If you were on this Earth Moon line, which is basically like, you know, this line between the Earth and the Moon, then what you would see is that, like, you know, some places of the Earth are being pulled faster than other places of the Earth. And if you did this math for the entirety of the Earth, you find that these two bulges form along this Earth-Moon line, and that is tides. It's actually the fact that the moon is squeezing the Earth just like a giant hydraulic pump. The moon still does cause tides. It's just that it's a
Right.
misconception as to how it causes it. Um,
So the explanation of it. Okay.
yeah, so the explanation is slightly off.
Are there multiverses? Do we have more universes than our own universe? Or is it just one universe that is our universe? And if it is, then what is there outside, perhaps like let's say 1 kilometer out of our universe? What exists out of our universe?
Yeah. So let me start off by answering that first question. Are there multiverses? And I actually couldn't see why not. Like, I couldn't see why not we would have, like, you know, multiple universes. And the reasoning for this is just the fact that, like, you know, our understanding of the universe has expanded so much since the past 500 years. No, actually, since the past 2,000 years. We actually started off with just one planet. Then we started off with, you know, one star that was our sun, and then we expanded to multiple stars, multiple galaxies, and then the next logical step would probably be multiple universes. The reason why I believe it's the next logical step is because our entire scientific consensus is based on the core fact that nothing is special, right? The Earth is not special, the sun is not special, our galaxy is not special, so that means our universe must not be special either, right? Multiple universes does seem like a possibility, as it would allow us to come up with decent, like, you know, theories to explain, you know, why is the universe so finely tuned for life. And in this hypothesis, which, you know, connects with string theory as well, in this hypothesis, the universal constants, such as the speed of light, are selected at random in all these multiple universes, and we just happen to be in the universe that has the right conditions to support life. As of now, however, we do not have direct evidence for multiverses. Now, you raise an interesting point about being outside the universe. According to general relativity, complex simulations, observations, and more, the universe is extremely flat, and astronomers think that the entire universe, is infinite. This could be rather problematic at first, because the thing is that we've all heard of the Big Bang, and the Big Bang states that the universe was created, the universe was created 13.8 billion years ago. But how could an infinite universe, a universe infinite in size, possibly condense down into, you know, a finite size? It's just not possible. How does that work out? And so when scientists use the term the universe, they really mean the universe which we can see, which is the observable universe. And this observable universe is roughly 93 billion light years across. The Big Bang states that the observable universe was once really, really, really small. And technically, the observable universe does have a boundary. But what about the entire universe? Well, if it's infinite in size, it probably doesn't have a boundary. But astrophysicists have been using their big brains and have actually been able to use fancy geometry to develop ways of visualizing the entire universe on a piece of paper. One such example is the Penrose diagram. In such a fashion, mathematicians have technically come up with a boundary, a mathematical boundary for the entire universe.
Fantastic, just great answer. Okay, let's get on to the next one then. And we've briefly touched this point already, but what do you think is the future of humans? Will we ever be able to travel outside our solar system or our galaxy? And in order to travel that far distances, would we ever be able to build machines like the warp drives or the fusion propelled engines that can travel near to the speed of light?
So, let's start off with a bit of history. And so I'll just quickly mention the fact that, like, I think the future of humans is looking great, only if we don't screw up human-created issues. And what I mean by that, I mean pandemics such as the coronavirus. We kind of screwed that one up. But once these issues are solved, then we can begin to colonize the solar system and beyond. Now, as a bit of history, there's actually this like really cool infographic, which I like to call, and basically it's like a doomsday clock. They call it the doomsday clock because it basically shows the rough amount of how close we are to destruction, total human annihilation. And so the time on this clock, by the way, is completely arbitrary. It could mean a couple of years to a couple of minutes to a couple of seconds. The time is completely arbitrary. But essentially, it's like a weird measure of how close we are to human extinction. And just recently, I believe we did hit a low in terms of how close we are to nuclear Armageddon. And that was actually because of the fact that there's climate change, but then there's also ignorant people in power. And so
Right.
people who did not who do not appreciate science and stuff like that. And so that's a great measure to see will humans actually make it to that glorious future of colonizing the entire solar system. But overall, I'm thinking things are going to look up. Now, the problem with government space organizations is that they are effectively controlled by the government, which is not good, as space government organizations can, change their ideas depending on which political party is in power. This means that space government organizations won't be able to accomplish that much in space. In fact, we can already see that with NASA. NASA hasn't been accomplishing a whole lot too much in space over the past few years. Yes, they did send the Perseverance Mars rover to Mars, and they did send the Mars helicopter to Mars as well. But most of their money is actually, most of the funding which they get is actually just being fueled into private companies such as SpaceX and Blue Origin. And so, now what we're seeing is we're seeing this privatization of space. And this is where private companies are getting in on all all the profit, and they're making money out of doing space ventures. So for example, another example would be Virgin Galactic and Richard Branson trying to get people to space as well for space tourism. And we actually need more competition of this because otherwise we won't get to space faster. An example of that is during the Cold War. Yes, the Cold War was a terrible time, but the Cold War actually led to the development of so many new technologies, such as the internet. And so we need more of that competition. Our first colony would actually be on the moon. So our first space colony would actually be on the moon. And NASA has already provided an outline as to how they will achieve that through their Artemis program. And NASA will work with private companies such as SpaceX to build landers, rovers, and other equipment to bring humans back to the moon. Now, moon rover missions are already identifying places where there is ice on the moon, and they will set up bases near there. For one example of that was the Chandrayaan-2, which unfortunately crashed on landing, but was expected to do this type of research. Now, the key to getting a successful base is to continually invest in the base until the base is self-sufficient. It can support itself, and once the base can support itself, it can then continue to grow and then export materials and technologies back to Earth. The next base after the moon will probably be Mars. Now, we've kept our eyes on Mars for so long, as one of the first places where we found evidence of water on its surface was Mars. Now, it has since then been a place of, like, space fantasy and stuff like that, and colonizing Mars has just been a big dream of ours. Now, one such problem of these colonies, such as the one on the moon and the one on Mars, is that, like, there's going to be a lot of low gravity, living conditions, and so this low gravity could cause bone loss at a rate, like, a few times faster than osteoporosis on Earth. Um, another candidate planet where we could colonize is that we could colonize Venus, for example. And Venus is a great planet because it's got a similar gravitational, gravitational pull to that of Earth, which means that bone loss will happen at a much slower rate. The problem is that we need to terraform Venus so that it's habitable for us humans, because currently it's kind of hell. It's very much hell. I'll just point that out. In terms of colonizing other star systems, I think we're just, probably a few hundred years away from that. And I think once we develop fusion technology, then we will start to colonize other star systems and colonize the solar system much more efficiently and much more quickly, and be able to do tasks within the solar system, such as building Dyson spheres and stuff like that. Now, in terms of the future of humans and how they will progress through that advanced civilization, those advanced civilization stages, I'll just briefly mention what those advanced civilization stages actually are. So we've got Type 1, Type 2, and Type 3 civilizations. Type 1 civilizations can control and gather the energy of their entire host planet and the starlight that actually hits that planet. A Type 2 civilization can control the entire energy output of its host star, and Type 3 civilizations, well, they can control the entire galaxy. Now, we humans do not even fall under the Type 1 civilization category, which kind of makes us look pathetic to any advanced civilization. But according to great think tanks, including Michio Kaku himself, we will reach Type 1 civilization within the next 100 to 200 years, Type 2 civilization within the next 1,000 to 2,000 years, and then the galactic civilization stage from the next 100,000 to 1 million years. So yeah, we've still got a pretty long way to go. In terms of transportation, I've already mentioned some of the transportation systems we might be using. Such examples include fusion technology, antimatter drives, even Kugel Blitz drives. I'll personally let you know that there will certainly be no warp drives. Sorry.
Right. Great answer. And I think you've touched on the topic of Kardashev scale when you were talking about the Type 1, Type 2, Type 3 civilizations. As laid down by Michio Kaku, which was really exciting stuff. And I mean, we are just getting started here. Technology and space and research, we are just getting started. So we have a lot of time, to explore and go on to these kind of Kardashev scale. Fantastic. What is consciousness? And how did we acquire consciousness? If life happened by the accident of, a microbe eating another microbe out of the trillions of microbes eating other microbes, then how does consciousness came into being?
So, consciousness, very, very, very philosophical. In fact, this is a place where, sometimes religion even comes into play. So I know, for example, in India, there are a lot of religions centered around, what is consciousness and how can we, transition, to a state of consciousness where there is no memory or none of our memory or materialistic or mental, dreams or goals or ideas in mind. But as we all know, life did originally come from, non-conscious, molecules reacting in warm water. And so, in fact, that's what you mentioned, Vivek. You mentioned that, you've got, a eukaryotic cell, and that once upon a time ate a mitochondria. And so what happened was that, the eukaryotic cell didn't digest that mitochondria, but instead kept it so that, it could produce energy for that cell. And it's been that way ever since. Um, Consciousness is actually something you cannot really define very clearly. Now, some people might believe that consciousness is something to them, while others might think it's something completely different. Now, let me provide some examples of that. Now, for example, an anesthetist, to an anesthetist, consciousness might be something essential to keeping a person alive. To them, without consciousness,
Mm.
well, you are not well, you. Now, to some other
Yeah.
scholars, consciousness has various forms. The first is wakefulness, followed by other forms. And consciousness is simply a dimension where no memory or no materialistic or mental forms influence it. According to some, consciousness is something with no boundary, no area. And in fact, I'd like to hear on your definition of consciousness. So, what is your definition of consciousness?
I think how I understand consciousness is something which is very unique to an organism, something that gives you a perception of feeling, uh, and emotions. So without consciousness, we could still be living like plants or other insects or organisms, but we might not be able to perceive life as it is today. So that's how my perception of consciousness is. And you've said it right. I mean, we're still researching on how exactly we got it. I mean, it is
Yeah,
one of the biggest topics of research today.
yeah,
Yeah,
exactly.
yeah, fantastic, Rudra. That is just mind blowing stuff. What you're sharing here. Let's get on to the next and continuing with our philosophical questions and discussions. Um, what is reality? Are we living as we see it, or because of our lack of comprehension of looking outside the three-dimensional world, we don't even know so many things that are around us? What do you think?
So, like, I think I've heard, Neil deGrasse Tyson mention something about, what is reality, and then he was just, going on a loop. Essentially, he was like, we're living in a simulation, in a simulation, in a simulation, and so on and so forth. I don't want to say that like 69 times, but many, 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 many thinkers have questioned about this over the past, few thousand years. Um, they thought that humans are so used to their current perception of reality that showing them, the much more truer reality, it will only leave them in disbelief, but will and will also confuse humans and bring them into chaos. And so you can
Right.
see this stuff in, movies such as The Matrix. They explore these key concepts about, what is the true reality, simulations, among other things. And in fact, this original idea of us not being in the true reality, I believe one of the earliest examples was from ancient Greece by a philosopher called Plato. Now, Plato, he came up with a thought experiment called Plato's Cave. And imagine that there are prisoners chained up in that cave, such that they cannot see each other, and they can only look at a smooth wall in front of them in the cave. There is a torch lighting the wall in front of them, and that anything that does come in front of the torch will produce a shadow on that smooth wall. Now, to these prisoners, these shadows, to them, they are reality. These shadows talk and walk and, do what they usually do, and to them, that's their reality. Um, like the in this Plato's cave, these prisoners have been chained up, ever since they were born. Um, yeah, but what happens when, one of these prisoners escapes? What happens if they move outside of the cave? Then they
Right.
would see, that, these shadows are not being caused by, these shadows are not talking, but rather it is the objects that create those shadows that are talking. And so these prisoners would be so baffled by this much more truer reality, that they might just go back to being chained up in that cave because of the fact that you know it's just more comfortable for them to believe in their own reality. Now, one hypothesis or idea is that we are in a computer simulation, and this was what Neil deGrasse Tyson and many
Yeah.
other thinkers were talking about. And this computer simulation is being rendered by advanced civilizations. Now, these aliens would be so advanced that they would be able to render simulations so detailed that they would render individual atoms, individual protons, neutrons, quarks, etc., up to entire intergalactic structures. Not only that, but they would also have to render billions of minds on Earth, all of which
Right.
have potentially infinite possibilities. For example, you know, for example, some decisions made by humans, they might not have happened, right? It just might have been like one of those probability things. And so,
Right.
this computer, the supercomputer, which the advanced civilizations have, must also take that into account. Um, and if that's the case, then we are just minions in a fancy computer. Now, however,
Yeah.
why would aliens actually want to run a simulation? Because it's a good idea to know what are the causes for even running a simulation in the first place. Now, one possible idea is that
Mhm.
these aliens are studying the ancient civilization. They're running what is called a historical simulation, learning about their past, when they were probably a very small planetary civilization. However, if that's the case, then maybe we have discovered so far that we might be a part of the simulation. In other words, the simulation might have wanted us to figure all of this out, that we might be a part of the
Yeah.
simulation and stuff like that. If we find out that we are not in the simulation, it could just be one of the outcomes from the simulation. In other words, the idea of us being in a simulation is unfalsifiable. But I couldn't see why not. We could already be in a simulation, given the fact that we're already on our way to creating hyper realistic simulations ourselves. So for example, we're seeing a lot of VR and AR being implemented in our phones. Also just in our every day-to-day lives, and so we're creating these hyper realistic worlds. And so this is one of the things which many people have been talking about, and that is that what if humans don't expand outwards into the solar system but expand inwards with technology and virtual reality and stuff like that. And so that's something which many people such as Michio Kaku, and other great thinkers have been thinking about.
Fantastic. So not just exploring outside into the universe, but looking within and then
Yeah,
going into that reality.
yeah.
Fascinating stuff.
And that could be a
And
reason why we
I
don't see aliens. That could be a reason why we don't see aliens.
yes,
Because
that's correct. Yes.
aliens just might see no benefit of actually going out into space and wasting all the time and resources when they could use that on exploring within, exploring quantum computing and other crazy, crazy,
Correct.
crazy stuff.
Amazing theories. Yes. Um, and I also follow Joe Rogan. He's one of the best podcasters in the world today. Um, there were times when he would invite these physicists and theoretical physicists, particle physicists, and during their talks, he would then, talk about this fact that would it not be true that because of the fact that humans are creating these technologies, which gets updated every time. For example, just take an example of an iPhone. Every year you get a better version or a better update. So similarly, if somebody would have put us into a simulation, they want us to become better by, in our own versions, so that there will be an end result to it. Think about a caterpillar who converts into a butterfly in its lifetime. So the caterpillar doesn't know that, it would transform into some other form. Similarly, maybe we humans or, the conscious beings do not know right now that we are inside a simulation and we are getting updated, making ourselves update every time we are going. I mean, look just 300 years back when we didn't have, all these tools and technology and everything else. But now we are there. And maybe in 300 years, we might accomplish much more greater things than we cannot see today. So perhaps, that could be right as well. Yeah.
Yeah, totally all
Yep.
possible.
Excellent. Yeah. Um, all right. So let's go on to the next one. Are we alone in the universe? There are trillions and trillions of stars in our observable universe, and we know that with every star there is a habitable planet in the Goldilocks zone. Hence, what is the probability of life emerging in those exoplanets? Can life as complex as ours ever possible anywhere else? Not microbes or plants or other one-celled organisms, but complex like humans who can think, who are intelligent, and who had an understanding and comprehension of everything around us. What do you
Yeah.
think?
So, what you actually touched on there was something called the Fermi paradox. And this paradox questions the lack of evidence of alien life in the universe. Now, this question has been asked for thousands of years, but only now are we actually starting to figure out that answer and actually make some, decent hypotheses. Now, let's start off with the arguments that suggest that aliens should exist. Now, as you have mentioned, based on data collected by NASA's Kepler Space Telescope, we know that there are roughly 300 billion stars in the galaxy, and there is roughly one planet per star. This means that in our galaxy there are 300 billion planets, of which roughly 40 billion are in the Goldilocks zone of their host planet. That means that there are 40 billion planets that are suitable to have liquid water on their planet, on that planet, and to potentially have life. Now, you might think, like, why is liquid water so important? Now, well, firstly, water is one of the most abundant molecules in the universe. Moreover, water is a molecule that has a high specific heat capacity, which means that it has high resistance to temperature fluctuations, allowing for stable temperatures and conditions to support the development of life. This is exactly what happened on Earth, and we believe something like this could happen on other planets. Anyway, 40 billion planet candidates of which life can form. Now, this is a pretty big number, so big in fact that it should account for even really tiny probabilities of spawning life on one of these planets. Even if we have a really tiny chance of spawning life on any one of these planets, there should still be thousands of civilizations in our host galaxy by now. And this is the point. Even if life, let alone intelligent life, is exceedingly rare, then we should still see thousands of civilizations. This argument was actually supported by a famous scientist called Carl Sagan. But if the probability of life is so small, and we haven't seen any direct evidence of life in our galaxy, then it makes life on Earth seem very special. Scientists hate special, any form of special. Our entire scientific consensus, as I mentioned previously, is based on the fact that nothing, not even the Earth, the Sun, or the galaxy, is special. This process which I described above of filtering through the planets to see which planets would be able to host intelligent life like our own is the process which Frank Drake used in his famous Drake equation. Now, uh, the thing is that in the Drake equation, there are two forms of factors. There are the astronomy factors, and there are also the biological factors. Now, we have a pretty good idea on the astronomy factors, but we do not have any idea about the biological factors. And so the thing is that when somebody uses the Drake equation to, determine how many alien civilizations or advanced alien civilizations there should be in our galaxy, most of the time what their guess is completely arbitrary. It could be anything. It could be any number. Also, think about it in this way. We only know of one instance of life in the entire universe, and that is the case of Earth. And it's really hard to do statistics with a probability with a sample size of one. There are solutions to the paradox, and one of them was, which I briefly mentioned, was that aliens do exist, but they just tend to not expand outwards and instead focus on virtual reality. But another idea is the idea of a great filter. A great filter is a filter that stops most, if not all, civilizations from making a long-lasting impact on their surroundings before wiping themselves out completely. Such great filters include climate change, nuclear war, pandemics, and more. The idea states that the rate of intelligent life forming is really high, so the probability that life will form on any given planet is really high. But the probability that life will wipe themselves out is also really high. If we are past the Great Filter, then that means we will most likely survive and colonize the entire galaxy. However, if the Great Filter is in front of us, then we're in for some trouble. Now, I think in the next few decades, we'll
Yeah.
start to find signs of biospheres on other planets. And these biospheres are basically atmospheres controlled by biotic processes, biotic life. Now, this will no doubt prove the existence of at least simple life. However, intelligent life will require a little bit more searching. After all, it took us 4.5 billion years of evolution to produce humans. Another idea is that life on Earth actually didn't even start on Earth, but rather it started in space. This is called panspermia, and if this is true, then life would only need to start once in the galaxy, before once in on any given planet before spreading out to the entire galaxy. Um, yeah, that's just pretty much all that I have to say on alien life, and also just the fact that please don't raid Area 51. Like, no. No, no. There's no
Okay.
alien life there.
All right, great. But you never know till you actually know.
Yeah,
So,
true.
yeah,
Yeah. There have been credible sources that have come forward, but again, it's never aliens until it's aliens. So, yeah.
right. So let me ask you on that topic, Rudra, where we mentioned that life on Earth actually started due to a glitch, right? So, although there are so many habitable planets, like you said, in the Goldilocks zone, merely on our galaxy only, right? So there are trillions of star systems and millions and billions of galaxies. So there could be more planets like ours. But then that glitch to happen, how big a probability is that? And without that glitch, can life actually exist or
Yeah.
come into being?
Yeah. So, I'll just briefly mention what that glitch actually is
Sure.
referred to. Scientifically, it's referred to as abiogenesis, and this is the point when
Mm,
non-life molecules, so molecules that do not exhibit properties of life actually then react and then form molecules and even cells that do resemble, properties of life, self-replication and stuff like that. And we personally actually do not even know, what the probability is of that happening. But even if that probability is like astronomically low, um, then
right.
we can just include all the planets in other galaxies, right? And so then that just makes the Fermi paradox even weirder. And I
Mm,
personally believe that the probability is definitely going to be low, but it's not going to be as low as we think it is, as we want, as as you're mentioning, being astronomically low, but
right.
it's definitely going to be low, but just not, we just don't know how low.
True. And because of our historical evidences and our research, we only know a set of things that we know, right? We still don't know so many other ways or scenarios in which life can propagate on other planets. So that'll be
Yeah,
great
true.
to discover and see in the
True.
future.
Yeah, exactly. So, an example could be instead of using carbon to form these really long carbon
Right.
chains, really long organic molecules, you could instead replace carbon with silicon, to create those
Okay.
long chains. But the problem with silicon is that even though it can form the same number of bonds as carbon can, and it can produce those same chains, those bonds between the atoms themselves will not be as strong as with carbon. And so,
Huh.
if we were to find life on other planets, most likely it will probably be carbon-based life. And we would
Right.
consider carbon-based life similar to us.
Fantastic. Great explanation. Loved it. All right. Let's go to the next one then. What is the meaning of life and why are we here in this universe? Or is there is no meaning? I mean, and it is just pointless.
So, I'll just give this a long, hard thing, but
Right.
personally, I think this is up to anyone's interpretation. If you're watching this, you probably have your own interpretation on what the meaning of life is. Um, To me, I think the meaning of life is to simply appreciate the universe which we live in. And without such a finely tuned universe, we would not exist. And as a result, there would unfortunately be no one to observe the beauty of this universe. And what I'm actually touching on, if you do want to learn more about this principle which I'm using, it's called the anthropic principle, if you do want to learn more. But I think we live in a golden age of astronomy. And we live in this golden age of astronomy where we know so much about the universe, but we still also have so many mysteries to solve. Um, More and more people are actually getting into astronomy and astrophysics, and it is becoming more readily available to people like yourself. And this is thanks to the internet and other technologies, but also the willingness by teams such as the team from the Molonglo Observatory Synthesis Telescope, from NASA, from other space organizations, willing to put their data out for people to analyze. Now, I really
Mhm.
like this quote from a filmmaker and YouTuber who goes by the name Melody Sheep, and it goes like so. The expansion of the universe will make distant stars invisible, and the night skies will go dark. Perhaps life in the future will ask, what was it like to live in the universe's early days? We are lucky enough to know the answer. All we have to do is look up.
Wow, so inspirational and such an amazing thought. That's a great way to end our discussion. Rudra, what was your opinion of this podcast, and what will you take back, and how? I mean, what is your overall experience of it?
So, my experience of this podcast is that, like, it's a great show. Vivek, you're a really engaging person. Really like all the work you're doing. Um, and I just feel like we need more of this stuff where we can directly
Yes.
talk to the experts. I myself am not an expert, but we can directly talk to the experts and sort of learn more about both science and artificial intelligence, as there's some of the things which are really intriguing us very recently, especially during the coronavirus pandemic. And so yeah, it's just like a really interesting way to talk to people as well. So thank you once again, Vivek.
Fantastic. Thank you, Rudra, for coming onto the podcast. You have a
Thank you.
great day. Thank you for listening to this podcast. Please support this podcast by liking, commenting, sharing it with your friends, and also subscribing to this channel. Thank you, and we'll see you next time.